Hello, this study seeks to model the electric energy generation in ERCOT during the extreme weather events of this last February. It also discusses renewable energy and the impacts it has on grid reliability. During February, this is what millions of Texans saw, a blackout. These blackouts cost billions of dollars in economic damages, and hundreds of lives were lost because of them. The February blackouts had several different causes. The primary triggering event was the extremely cold weather. However, Texas has almost doubled in population since 1980. There was insufficient generation available within ERCOT. Too many units were out on planned outages. Renewable energy was practically unavailable at times during the blackout. And because it's a blackout, we don't actually know what the true demand was for energy at that time. The conventional power plants had issues with fuel supplies. This took the form primarily of natural gas lines freezing up due to entrained water vapor. The water vapor froze and the supply lines could not be cleared. Also, some steam plants were not prepared for the cold. Return lines for water and such were blocked because they were frozen. Renewable energy under normal circumstances, and we can look at about February 4th on this chart, can account for as much as half of the energy used in Texas at a given time. However, if we look around February 15th, we can see that the renewable energy lines, and that's down at the bottom there, the dashed line is solar and the dotted line is wind, account for a minuscule portion of our power, at times drifting below 1,000 megawatts. When true demand was probably, on this chart it shows it is approaching 70, and it might in fact have reached 80,000 megawatts. So how do we prevent more blackouts? Well, first we have to define what demand was needed, or what was the total demand. Remember, we don't know that. Second, we have to decide how much renewable power is allowed at a time on the grid, because it does present a risk. Third, we need backup power, both for the renewables and the conventional sources. Weather is a primary driver of our demand, and so we used NOAA weather from many different stations to supply our model. These stations are primarily at airports, both commercial, military, and general aviation. It's hourly data, although it's missing some data. Missing data was imputed with a MICE routine. A geographically diverse set of stations within ERCOT were selected, with care being taken to select something for every population center, since they are the demand centers. Instead of straight temperature data being used, a score was created where the absolute difference between 72 degrees Fahrenheit and whatever the current temperature was used in the model. Generation data from ERCOT was found in their fuel use reports. This report shows all the power generated by gas combined cycle, coal, nuclear, wind, and solar. The report was in an inconvenient format and had to be normalized to hourly data, and the daylight savings times effects had to be addressed as well. However, the report has no missing data. It's complete data. Power data has 3 seasons. 24 hours daily cycle. If you're at 7 o'clock tonight, it's going to look like 7 o'clock tomorrow. A weekly cycle. A Wednesday's power consumption will look like next Wednesday's power consumption more than it would look like a day on the weekend. And finally, a yearly power cycle. Power use in June mimics the power use next June, not the previous January. 3 different time series models were used to try and model this data. An ARIMA model with regression and seasonality, a linear regression time series model, and dynamic time warping. The AREMA model included regression and seasonality. Unfortunately, AREMA can only handle one season. In this case, we use daily. The model predictions quickly regress to the mean, about 40 gigawatts at a time. However, under the model or under the rubric that all models are wrong but some are useful, AREMA does show us one thing. AREMA clearly shows the 3 seasons. We see here peaks every 24 hours on the left in our daily peaks. We see weekly peaks at 168 hours in lags. You can see every 7 of those peaks line up. And finally, every 8,760 hours in lag, we see a peak as well. So we see the 3 seasons with the AREMA models looking at the ACFs of the residuals. Next, the time series linear regression model. This model treats the seasonal aspects as categories. So we have a category for hours, and these are one-hot encoded, days of the week, and months. The temperature data is regressed. This returns a useful prediction. We end up with a mean absolute predicted error of 6.41% when the full model is used. And we can see the results over here on the right hand with just a seasonal, in other words, just seasonal and trend, just looking at the power produced, we had almost a 10% error. Adding in our categories to handle the seasonal aspects of it, reduced that to about 9.5%. But adding in the temperature data got us under 6.5%. Here's a few days of the model prediction in the dark line. The dotted line is, the dark line is the actual power consumed. The dotted line is the predicted, and the gray area is the confidence interval. And we can see within, except for a few instances, the actual demand pretty closely follows our model. Dynamic time warping still to be done. So what have we learned? The linear regression model does provide useful predictions. Accurate forecast of temperature data is extremely important. Our model is only as accurate as the underlying forecasted temperature data. We can improve our model, probably getting better data using mice to do a better job of imputing the data. And we could try tweaking the seasonal categories and see if that could be effective as well, lumping in holidays, for instance, with weekends, that sort of thing. Ethics. We have a fundamental conflict between reliability and green energy. Currently, green energy simply is not reliable. The impact of the blackouts are many. The economic loss, and loss to life and limb. Long-term grid reliability is something to consider as well. A society that does not have reliable electric power, this impacts the sort of economic activity that can occur. Manufacturing becomes difficult, all sorts of other impacts are occurred. And we really can't say, oh, let's not consume fossil fuels here for our manufacturing, let's do that in some other country. The CO2 is still generated. It doesn't matter if it's here or there, so farming it out to another country is not a viable option. Conclusions. The estimated peak power that was needed during the recent blackouts was 80 gigawatts. This would represent a system high. We need to put a moratorium on new renewables until we understand better how to integrate them into the grid. We need to focus on preventing blackouts in the short term. This can take the form of scheduling our outages better and also apply lessons learned. Heat trace tape on supply lines that froze, additional equipment to ensure the reliability of the natural gas supplies. Long-term, better temperature data is needed for better models, and it's good to think of the February blackouts not as a black swan, but as a canary in the coal mine. They could precurse more serious problems. Thank you.